Welcome to another podcast from the Rooster Podlog. Today we're diving into the world of Apache Spark and real-time stream processing.
That's right. We'll be exploring how Spark analyzes data as it arrives. So it makes it ideal for applications, that demand instant insights.
We've got some great sources to guide us through this, including articles and research papers that break down complex concepts into, digestible chunks. And to make things even more fun, we'll be using a WWE analogy to help visualize these ideas. So think of Spark as a commentator reacting to each move in a live match.
That's a great way to put it. Just like a commentator needs to keep up with the action, Spark needs to process data in real time.
But before we jump into the ring with Spark, let's clarify what stream processing actually means. You might be wondering how it differs from, traditional batch processing.
Well, imagine trying to analyze a wrestler's performance during a match, reacting to every move in real time. That's what stream processing is all about.
Yeah.
Instead of waiting for all the data to be collected, it allows you to analyze it as it comes in.
So it's like the difference between analyzing a wrestler's entire career after they retire versus providing live commentary during a match.
Exactly. And this live aspect makes stream processing perfect for applications where timely insights are crucial, like fraud detection or personalized recommendations.
Okay, that makes sense. But doesn't analyzing data on the fly require like a lot of processing power? How does Spark manage to handle like such a huge volume of data without lagging behind?
That's where Spark's distributed processing model comes in. It breaks down the workload across multiple computers, allowing it to process massive amounts of data in parallel. We'll dive deeper into Spark's architecture later, but for now, just think of it as a tag team match, where each wrestler handles a specific part of the action.
So Spark is like a well-coordinated tag team working together to analyze data in real time.
Precisely. Now let's look at a simple PySpark code example to illustrate the difference between batch and stream processing. In batch processing, we read a static file of data, process it, and then the code ends. In streaming, however, the code keeps running, continuously reading from a live data source and processing the incoming data.
That's a clear way to see how stream processing differs from traditional batch processing. The code never stops running, just like a live WWE match.
Right. And this brings us to a crucial aspect of stream processing, the concept of time. In the world of streaming, we're not just dealing with when we analyze the data, but also with when the events actually occurred.
So Spark needs to keep track of both processing time and event time. That sounds like it could get complicated.
It can. Think of it like this. A wrestler might execute a move at 9:15 p.m., but viewers watching on a delayed broadcast see it at 9:11 p.m. The commentator needs to know both times to provide accurate commentary. Similarly, Spark needs to consider both the actual time of events and when it's processing them to maintain data consistency.
This raises an important point about how Spark deals with time. Can you elaborate on the challenges of handling event time and processing time in real-time scenarios?
Absolutely. One of the biggest challenges is that events often arrive, late or out of order. Imagine a chaotic Royal Rumble match where wrestlers enter at unpredictable times and form unexpected alliances. Streaming data can be just as unpredictable.
So Spark needs to be prepared for late arrivals and unexpected data patterns, just like a commentator handling a surprise Royal Rumble entrant.
Exactly. And to address this challenge, Spark employs techniques like windowing and watermarking. We'll get into those a bit later. But for now, just understand that these techniques help Spark manage the uncertainties of time in stream processing.
Before we delve into those techniques, I'd like to shift our focus to the real-world impact of all this. What makes stream processing so exciting is its wide range of applications, from fraud detection and personalized recommendations to monitoring millions of IoT devices in real time. It seems like stream processing is everywhere.
It is, and it's only growing in importance as businesses increasingly rely on real-time insights to, make decisions, just like WWE producers analyze crowd reactions to adjust storylines and feature popular wrestlers.
So it's about keeping up with the action and adapting on the fly. But all this real-time magic wouldn't be possible without a solid foundation. Let's take a step back and understand the roots of distributed data processing. Can you tell us about MapReduce, the precursor to Spark?
Certainly, MapReduce was like the old-school reliable wrestler who paved the way for today's high flyers. It broke down data processing into two steps: map, where individual data points are processed, and reduce, where those results are aggregated. Think of individual wrestlers training, mapping, and then coming together for a championship tournament, reduce.
So MapReduce provided a way to um, handle huge data sets by distributing the workload across multiple computers, making it scalable and fault-tolerant.
Precisely. And Spark builds upon this foundation, offering a more flexible and efficient approach to distributed data processing. It's like the evolution of wrestling, with new techniques and styles emerging, while still, respecting the traditions of the past.
That's a great way to connect the evolution of data processing to the world of wrestling. Now, let's talk about how Spark handles the complexities of distributed and stateful stream processing. When we talk about distributed stream processing, it's like a tag team match, where each wrestler only sees part of the action.
Right. To understand the full match, you need a system that can combine all these partial views. And that's what distributed stream processing does. It splits the data stream across multiple nodes for parallel processing. It ensures that each part of the data stream is processed concurrently, leading to faster overall processing times.
But what about situations where we need to remember past events to understand what's happening now? That's where stateful stream processing comes in, right?
Yes. Think of it like a wrestling referee, keeping track of fouls throughout the match. Stateful stream processing maintains that historical context. Here's a PySpark example that illustrates how you can define a function to update a state based on incoming data. In this case, it's keeping track of points earned by wrestlers during a match.
So Spark can not only process data in real time, but also remember past events, enabling it to perform more complex analyses. Now, with this foundational understanding, let's finally introduce the star of the show, Apache Spark. What makes this engine so special for handling both batch and stream processing?
Spark's initial claim to fame was its in-memory processing model, which significantly speeds up data processing by storing data in RAM. Instead of relying on slower disk access, this is like a wrestler having lightning-fast reflexes, allowing them to react instantly to their opponent's moves.
And Spark's functional programming approach via RDDs, or resilient distributed datasets, further enhances its power.
Exactly. RDDs are the fundamental data structures in Spark. Think of them as the fundamental wrestling moves, the basic building blocks for more complex operations. They are immutable, meaning they can't be changed once created,
Right.
which ensures data consistency and forms the basis of Spark's fault tolerance.
Then came Spark SQL,
Yeah.
which introduced data frames and datasets, making data processing even more user-friendly.
Right. Spark SQL provides a higher level abstraction on top of RDDs, allowing you to work with data in a more structured and familiar way, similar to how SQL databases operate. This is like the high-flying acrobatic style of modern wrestling, accessible yet, incredibly powerful.
And just like wrestling has evolved, so has Spark's approach to streaming. Can you tell us about the two main APIs it now offers?
Certainly. Spark now offers two main APIs for stream processing: Spark Streaming, the original microbatch-based approach, and structured streaming, built on the more modern foundation of Spark SQL. Think of it like the shift from the Attitude Era to the PG era in WWE. Different styles, different approaches, but both serving the same, core purpose: entertaining the fans.
Interesting. So what are the key differences between these two approaches?
Spark Streaming, the veteran, processes data in small batches at regular intervals, while structured streaming treats streams as unbounded tables, allowing for continuous processing.
The example here highlights how to use structured streaming to read data from Kafka, process it, and then write the results to a console.
Now, regardless of which API you choose, understanding Spark's stream processing model is crucial. It all starts with sources, where the data comes from. Think Kafka files or even live data from websites.
Then we have sinks, where the process results go, perhaps a database, another application, or a dashboard for visualization. It's like the entrances and exits of the wrestling arena.
Exactly. The data flows from its source through Spark's processing engine and finally to its destination. And remember, Spark treats these data streams as immutable, meaning transformations create new stream without changing the original.
So it's like a wrestler's character evolving over time. Their past is still there, but they've, taken on a new persona.
A perfect analogy. Now, to get the most out of stream processing, we need to talk about window aggregations.
Right. These allow us to analyze data over specific time intervals Imagine analyzing a wrestler's performance not over their entire career, but within specific matches or even rounds.
Precisely. Spark offers two types of windows. Tumbling windows, which are fixed and non-overlapping, like distinct matches in a tournament. And sliding windows, which overlap and move forward, like highlight reels that may include, parts of multiple matches.
This PySpark code snippet demonstrates how to define both tumbling and sliding windows to analyze streaming data.
And to manage the uncertainty of late arriving data, Spark uses watermarks. It's like a countdown timer for wrestlers entering the Royal Rumble. Once the watermark passes, any late data is considered eliminated and not included in the analysis.
This code example shows how to add a watermark to a stream, ensuring that only data within the specified time window is considered.
With the basics of the stream processing model in place, let's move on to the architectural side of things.
Now, just like WWE has different venues for its events, Spark can run on various cluster managers.
That's right. We have standalone mode, Spark's built-in manager, and other popular options like Yarn, Mesos, and Kubernetes. These are like the event organizers who make sure everything runs smoothly.
Speaking of running smoothly, data delivery semantics are crucial. Spark offers at least once and exactly once guarantees for data processing.
At least once ensures that every wrestler gets their entrance, even if some come out, twice by mistake. Exactly once is like a perfectly choreographed show,
Yeah.
where everyone appears exactly when they're supposed to.
This is a trade-off between reliability and complexity. Exactly once is ideal, but harder to achieve.
And finally, let's touch on micro-batching versus continuous processing.
This PySpark code shows how to configure Spark for both microbatch and continuous processing modes. Microbatching processes data in small chunks at regular intervals, while continuous processing handles each record individually as it arrives. It's like choosing between watching wrestling highlights or a live, uninterrupted stream.
Excellent. We've covered a lot of ground, from the basics of stream processing to Spark's streaming model and architectural considerations. Welcome back to our deep dive into Apache Spark for real-time stream processing. Before we moved on, we were discussing Spark's streaming model and the architectural choices involved.
Right. We talked about how Spark acts like a well-coordinated tag team,
Yeah.
breaking down the data processing workload across multiple computers.
Exactly. And now let's shift gears and explore how Spark tackles the challenge of fault tolerance, ensuring our streaming applications can handle, unexpected bumps in the road, just like a wrestling match needs backup referees in case one gets taken out.
So Spark has mechanisms in place to recover from failures without missing a beat. What are these mechanisms and how do they work?
At the heart of Spark's resilience model are resilient distributed datasets, or RDDs. They form the foundation for fault tolerance by being immutable, meaning they cannot be changed once created.
So any transformations on an RDD result in a brand new RDD, preserving the original data. It's like a wrestler adding a new move to their repertoire without forgetting their classic techniques.
A great analogy. RDDs also maintain lineage, which is like a detailed history of all the transformations that led to its creation. This allows Spark to, retrace its steps and reconstruct lost data partitions in case of failure, like having a meticulous record of every step in a wrestling match, allowing you to rewind and replay any part if needed.
That makes sense. But what kind of failures can Spark actually handle? Can it recover from individual task failures? Or even more serious failures, like a complete driver crash?
Spark is designed to handle various types of failures. In case of a task failure, maybe a worker node goes down, Spark simply retries the task on a different node. So if a wrestler gets injured mid-match, a replacement can step in without disrupting the entire event.
So Spark can easily recover from individual task failures, but what if a whole stage of the processing pipeline fails, affecting multiple tasks?
In this case, Spark leverages the RDD lineage to recompute only the affected stages. It's like restarting a specific round in a boxing match if something goes wrong,
Yeah.
without having to replay the entire fight.
That's impressive. But what about driver failures, which are more serious? As the driver orchestrates the entire Spark application, can Spark recover from such critical failures?
To recover from driver failures, Spark uses checkpoints, which are like saving points in a video game. By setting up checkpoints, Spark periodically saves the state of the, streaming application, allowing it to recover gracefully from driver failures. So, if the entire system crashes, we can resume from the last checkpoint. instead of starting from scratch.
So this PySpark code snippet shows how to enable checkpointing for a streaming query, specifying a location to store the checkpoint data.
Now, as we conclude our discussion on Spark's resilience model, it's crucial to remember that fault tolerance is not just about handling failures, but also about ensuring data consistency. So even if a failure occurs, we can be confident that the final results are accurate and reflect the true state of the data stream.
That's reassuring to know. So Spark not only handles failures gracefully, but also maintains data integrity throughout the process.
Exactly. And with that, we've covered a lot of ground in understanding how Apache Spark makes real-time stream processing not only powerful, but also reliable and resilient.
Welcome back to the final round of our deep dive into Apache Spark for real-time stream processing. We've explored Spark's, incredible ability to analyze data on the fly, manage time complexities, and gracefully handle failures. Now we get to the main event. Spark streaming versus structured streaming.
Exactly. Think of it as a classic wrestling showdown where, each contender brings their unique strengths to the ring. In one corner, we have Spark streaming, the seasoned veteran, built on the concept of microbatching. And in the opposite corner, we have structured streaming, the agile newcomer, leveraging the power of Spark SQL.
Okay, let's break this down. Spark streaming, our veteran, uses microbatches. What does that mean in practice, and what are its advantages?
Spark streaming processes data in small batches at regular intervals, providing a reliable and well-understood mechanism for real-time analysis. Think of it like a classic wrestler, relying on their signature moves, delivering consistent performance with every match. It's been battle-tested in countless production environments, and offers excellent fault tolerance through its RDD lineage and checkpointing mechanisms.
So Spark streaming sounds like a solid choice for applications that, need stability and predictability.
Oh,
Are there
yeah.
any downsides to this approach?
Well, its micro-batching approach introduces latency, as you
Yeah.
have to, wait for a batch to complete before seeing results. It's like waiting for a commercial break to end before the action resumes in a wrestling match. And while Spark streaming is powerful, it can be less expressive and flexible compared to newer approaches.
So it sounds like structured streaming, our agile newcomer, might address some of these limitations.
That's right. Structured streaming treats data streams as unbounded tables, allowing for continuous processing and lower latency. It inherits the, power and expressiveness of Spark SQL, making it easier to perform complex transformations and aggregations.
So it's like a modern wrestler incorporating diverse techniques from different styles to outmaneuver their opponents.
Excellent analogy. Structured streaming also simplifies the development process. With its higher-level API and seamless integration with, Spark's ecosystem, it offers faster insights and greater flexibility.
But what about reliability? Can structured streaming match Spark streaming's resilience when it comes to, handling failures?
Absolutely. Structured streaming also leverages checkpointing and provides strong guarantees for data consistency, ensuring your streaming applications can recover gracefully from failures.
So it seems like structured streaming offers the best of both worlds:
Yeah.
speed, flexibility, and reliability.
It does. And as Spark continues to, evolve, structured streaming is becoming the preferred choice for new streaming applications. However, Spark streaming remains a viable option for existing workloads or specific use cases where its micro-batching approach aligns better with the requirements.
So for our listeners who are just getting started with, real-time data processing, how should they choose between these two approaches?
Choosing the right API depends on your specific needs. If low latency is crucial and you're comfortable with SQL, structured streaming is, a great choice. But if you have existing Spark streaming applications or prefer a more established approach, Spark streaming is still a solid contender.
It sounds like both Spark streaming and structured streaming have their own, unique advantages, and the best choice depends on the specific requirements of the application.
Exactly. And regardless of which API you choose, remember that Spark provides a powerful and resilient platform for tackling the challenges of, real-time stream processing. It allows us to make sense of the constant flow of information in today's world.
We've learned so much about Spark in this deep dive. We've explored how it analyzes data on the fly, manages time complexities, and gracefully handles failures. We've even delved into the differences between Spark streaming and structured streaming, understanding their strengths and weaknesses.
And now it's your turn to explore further. Think about how these concepts can be applied to your own work or interests. Perhaps you're interested in analyzing social media trends as they emerge, predicting traffic patterns in your city, or even personalizing your workout routine based on your biometrics. The possibilities are truly endless.
Thank you for joining us on this deep dive into the exciting world of Apache Spark and, real-time stream processing. We hope you've gained valuable insights and are inspired to explore the power of Spark for yourselves. Until next time, happy streaming.